colleagues, and friends. I'm Hua Qian from Southeast University. So it's my great pleasure to host this session. Also welcome of you to this JBDE Frontier Forum. The JBDE Frontier Forum is an important academic platform of the journal, aiming to bring together experts from around the world in the fields of building and environmental science and share result achievement. Today, we are truly honored to have Professor Hunyuan Chen from the Hong Kong Political University as our distinguished speaker. Professor Chen has long been dedicated to exploring ventilation, thermal comfort, indoor air quality, building environment, building energy, and he will deliver an excellent talk entitled Generative AI-driven architectural design, automating transition from concept to building energy simulation. When I was a postgraduate student, I relied on Professor Chen's paper to guide my CFD simulations and validate the results. At that time, CFD was a pioneering tool. Data foundation is the main reason I agreed to host this platform today. Now, Professor Chen is once again standing at the forefront of cutting-edge tools, the generative AI-driven. So, in addition, we are honored to have Professor Darren Robertson from the University of Sheffield and Professor Sun-Min Yong from Hunyuan University serving as discussion guests for this forum. Before we begin the presentation, I would like to take a moment to briefly introduce the JBDE and Professor Chen. The journal of the JBDE, founded in 2023, is a golden open access journal. The JBDE focused on cutting-edge sustainable technologies, intelligent buildings, high performance building materials, structural design, building energy efficiency, and indoor environmental quality. The target of the JBDE, the impactor is 7, as shown here, 7. And the good news, the JBDE will waive 80 APCs before 2029. That means it will be free to submission. And the JBDE also have the official WeChat account just showed on the right bottom. They showed the assistant editor WeChat and WeChat official account and academic exchange group. So if you like, you can scan the QR codes. Okay. So this showed the editorial board member of the JBDE. The JBDE joined led by 2 editors-in-chief, Professor Mo Zhang from Huazhong University of Science and Technology, who is globally highly cited scholar in intelligent construction and digital twins, and recipient of the National High-Level Talent Grant. And Professor Xiangyu Wang from East China Jiaotong University is a highly cited researcher, ranked first globally in intelligent construction, academicians of the European Academy of Science, academician of European Academy of Science and Arts, and also Dr. Zheng Bosheng from Curtin University served as executive editor. There is an international team of the 8 associate editors, as shown in the slides. To ensure the highest academic standards, JBDE has established an international editorial board. Currently, we have 34 scholars from 9 different countries serving on board, brings diversity expertise and global perspectives to the journal, including Hunyuan Chen. And in addition to the main editorial board, this is also a dynamic young editor board. The journal have 39 early career scholars from universities across 7 countries. To promote a global academic exchange, JBDE also launched two major series academic activities this year. First is the Frontier Forum, as shown today. So they have successfully hosted nine sessions. Second, to provide a platform for early and middle career researchers, also launched an emerging forum in October. So far, the JBDE Forum series has received over 180,000 views worldwide. Also, the JBDE is an official journal of the International Society for Smart Construction and Production. This is show the founding precedents of the SCP. So SCP is an international professional society dedicated to advancing smart construction, production technologies, and sustainable infrastructure through global cooperation. The society was confirmed by 3 world-renowned leaders in engineering and science. The founding leadership team brings together with Professor Hunyuan3D-2.5, Professor Vijay Singh, Fellow of the U.S. National Academy of Science, and Professor Claude Burgermeister, Fellow of the German National Academy of Science. Next, I am very pleased to introduce today's keynote speaker, Professor Qingyan Chen from the Hong Kong Polytechnic University, China. Qingyan Chen is the director of the PolyU Academy for Interdisciplinary Research and a chair professor of Building Thermal Science and a global STEAM professors at the Hong Kong Polytechnic University. He is also professor emeritus of mechanical engineering at the Purdue University, USA, and served as the editor-in-chief of Building and Environment from 2008 to 2024. He received numerous awards from different international organizations, including recent election to Fellow of the Royal Society. I searched the internet. I find that he is the first HVAC scientist to be elected for the Fellow of the Royal Society, which is widely regarded as one of the highest honors in the global science. So Professor Chen is very, very famous in the HVAC system area. Next, also welcome two discussants to join this session. First is Professor Darren Robinson from the University of the Sheffield, UK. And Professor Robinson is chair in architecture and urban science, whose pioneering research operates at the mutual intersection of science, social building, and urban physics. He is also elected fellow of IBPSA. He has earned numerous accolades, including CIPSE, Leverage Medal, and several Best Paper Awards. And second discussant is Professor Yong Sun Ming from Shenyang University, South Korea. Professor Yong is an associate professor in the Department of Architecture. He developed ontology and logic graph-based frameworks that can connect heterogeneous data, documents, models, and external knowledge to support reliable AI agents and decision support systems. So there, join the discussion panels will enrich the speech. So now we'll welcome Professor Chen to do the keynote speak.
Oh, thank you very much, Professor Chiang, for your very kind introduction. It's a great honor for me to give the presentation here. And this is the first time I try to do something online for this journal, and I hope it will work out. So the topic I'm going to talk about is how to use AI to do the building design and then simulate the energy consumptions in buildings. So let's look at the conventional building design. If you are a user, for example, like me, I wanted to design a office building here in Hong Kong. And then, of course, my first approach is to find an architect. And then architect will generate a number of conceptual design. And then ask me, well, are those design meet my requirements? And probably I will have some iteration with the architects and then finally identify a good design. And I say, yes, that's really the design I want. And this is a so-called preliminary design. So with the preliminary design, then of course, you can involve the engineers, etc., to get into these design details to generate the document for construction, etc., and let's develop the design. And again, from preliminary design to develop design, there's also needed several iterations because you will involve not only the HVAC engineers, you also have to involve the structural engineers, etc., because there's always some type of conflict. So this is a conventional approach. And in the past, many researchers have already tried to develop the computer-based design. And this is started actually before the AI became a available tool. So for example, about 10 years ago, many people just try to use this genetic algorithm, right? And you try to see, I have several building layout, shapes, etc., and which one will give me the least energy consumption. And it's, of course, not only the genetic algorithms, right? You could also just vary several parameters. For example, wall to window ratio. Or you could also think about the building design is not like matchboxes. You will try to see different type of shapes. And even the interior optimization, the layout could also be changed. So this had been doing for a while, but the progress has been rather slow before the AI errors. So about 2 years ago, when the ChatGPT 4.0 was published, then this becomes a reality. So what the ChatGPT can do for us? Because ChatGPT is a large language model. As you can see in this slide, this large language model is very knowledgeable because ChatGPT has read almost everything in the internet and they published materials. So it's in principle, I mean, it's really a super person who is very knowledgeable, has a lot of experience. You can name that, right? And then let's say that if it was a super person and then design a building seems is not very difficult. Then let's assume that I replace the architect I mentioned earlier by this LLM, and let's see if the large language model can design a building for me. But of course, when you communicate with this LLM, you have to use a prompt to do the job, which means that you use the language and to describe your need. And GPT, which already read all the images and text in the literature and all the database, and can quickly generate you the architectural design. So that's the idea. Okay, then let's see how it works out. So let's again just look at this flow chart. And I'm, again, is a user. And I still wanted to design an office building here in Hong Kong. And of course, I communicate with the LLM through the predefined prompt, which will say, yes, I am going to design a building with the certain size, etc., with a certain function. Then LLM will generate a design, but of course, which can be in a certain form, which could be code, all right? Then the code you can convert it into a 3D model. And then let's look at like conceptual design. And very similar to our interaction with an architect, you need the iterations because currently LLM might not always give you an optimal design. So you need to talk to the LLM and then to identify the most desirable output. So as soon as you have a desirable 3D building models, then you can use additional software or large language model like Ladybugs or Honeybee, and then convert this 3D model into the input, which could be used to calculate the energy consumptions in buildings, like EnergyPlus, right? And then, of course, you find out the energy use of that design might not be ideal. You wanted to conserve more energy, then you will, again, have another type of iteration and try to minimize the energy use. And sometimes you could also want to have a building design with a certain type of style. For example, I wanted to have a building design in a similar style like the famous architect Frank Gehry. So let's the process. Now let's see how this works out. So very similar to what you normally will do with a typical architect is 3 steps. All right. So the large language model is just like an architect. You have the conceptual design, which normally have an output is just a building machine. So it doesn't contain the details, and probably you don't have the windows and the structure in place. That's only the shape. Then when you agree on the machine, then you can work a little bit more details. For example, you will look at the floor layout. You know which floor you might want to, some floor is offices, some might be retails, some may be just storage, etc. That's the floor layout. Then you would look at what type of windows you are going to design. What is the window wall ratio, WWR? And that's any external shading element. And that's the preliminary design. But this preliminary design, again, has no systems into that. And even you don't know if the structure will stand because you have not involved the structure engineers. So only when you make it into develop the design, then you will have make sure the building will stand because you have the beam and columns and which the structure is sound. But you, in terms of energy simulation, which means you will have the HVAC system, you have the heating, cooling, ventilation, etc., and then which can be used to start the building of this design. Now let's take the one example here, and let's say my campus building. As you can see on the left side, this is a main building at the campus of Hong Kong Polytechnic University. So this is a real building currently in use. We call building M, with a total floor area of 16,000 square meters. It's a pretty big building, 18 stories high, with a total height of 75 meters. And then also have a pretty large window to wall ratio of 0.56. Okay, which means the window area is bigger than, it's a very big one, okay? 56% of the walls. On the right side, you can see this is the current building construction. All right, this building was built in 2001, 25 years ago, and has a lot of details. So we know almost everything, how this building was built, what's the current energy use, etc. And those are the details. But of course, before this building was built, probably we don't know those details. But with these details, at least I can compare with the design. I'm going to ask AI to do the job, and then compare with my current building performance, and then see if AI is doing a good job, okay? So let's the first step on the conceptual design. So this is the prompt I input into the large language model. Okay, let's say the language I use. You see, I wanted to design a building which is 16,000 square meters, 18 stories, and floor height of 4 meters. So it's exactly the same as my current building. But of course, the AI model, it doesn't know about this, okay? And then therefore, we could test how good this AI Claude can do that. This is the first AI model called Claude. So we know, we also give the side dimension, 40 meters times 37 meters. So it's a pretty square one, all right? And then the building itself is 21 meters long, 12 meters wide. This is the central core. Okay, so we gave a more or less like the current building. And now we give the AI an objective. This objective is to optimize the building design in order to achieve the minimal energy consumption. But of course, we still want to maintain the functionalities and the aesthetical appeal, which I like the building to be beautiful. But you can see this is the top right, top left. This is the first version of design. So Claude give me somehow. Let me see. I have something on the top which really hide myself. I cannot see. How could I move this? Okay, it's better I move it to the bottom. Okay. So you see, I use this Claude 3.7 Sonnet, which is large language model, and which generated 6 different type of buildings for me. And then when I look at the list, I actually don't like anything of this, because those 66 models is worse than the one we have, right? Although this Claude 3.7 has almost everything in its knowledge, because it doesn't look so nice. And therefore, I just say, well, please just generate alternative shapes. Then it go to the right one here. Okay, some improvement, but not that much. I mean, the building shape you can see here is a lot of conventional. So I said, well, please do something more, okay? Because this shape looks conventional to me. And then it generates something on this bottom right. Well, again, not that nice. So I tried 3 or 4 times, and it doesn't really improve. As you can see, this is a bottom left is the final one. Compared with the top left, there are not much difference, right? So this is a lot of disappointing. So when my students gave this design to me, and I said, that's not what I really want. Can we do something a little bit more? Because I have this building, this original design here, which has a pretty nice looking, and the energy use 286 is reasonable, and has a pretty big windows. That's the floor area. Now we look at the computer generated one, and then I just pick up one here, okay, because none of them really making me excited. So I just pick up one and then do the energy analysis. Maybe there's a reasonable background there why this Claude 3.7 generated this one. Maybe they will use less energy, right? Because the one on the left, the real one, might use more energy. So I do that and then convert it into the model, which can be simulated by EnergyPlus, which is an energy simulation program. Okay, and then I can run this EnergyPlus and get the energy use. So energy use turned out to be 273.3 kilowatt hours per square meter per year. Compared with the 286 in the current building design, well, there's some savings there, but not that much. But you can see the window to wall ratio has been reduced from 0.56 to 0.41, which means the window becomes smaller. So that the energy reduction might be caused by the reduction of the window area, because we know that Hong Kong is very hot and humid. If you have large windows, of course, you will use more energy. So that doesn't mean that this shape matters very much. Okay, but the floor area, because I gave the objective, say, design something about 16,000 square meters, and this Claude 3.7 generated a building of 17,000, well, close enough, right? But the building is not exciting. But anyway, then I give additional prompt to the Claude 3.7, and I say, well, current building design with the energy consumption of 273 is still pretty excessively high. So can you reduce that? And of course, computers say yes. I mean, AI say yes. And then generate something 271. I mean, reduce only 1%, less than 1%. But you can look at it here, the window to wall ratio, it becomes even smaller, 0.2. Okay, that's not exciting. And then I said, that's still too high. Can you do something more? But it seemed out not, right? As you can see, the final design is a different shape, and then the energy use is still 271. Those 271 seems is the sky limit, so cannot do anything further. But the window to wall ratio is still too low. Okay, so with this, you might conclude that the AI cannot do the job, right? Because the total energy consumption only reduced to 5.4%, but this window to wall ratio really reduced to the minimum. And therefore, I ask my students, say, well, current design, let's say that if it's acceptable, then can we do something to help on the systems, right? Now, that's interesting. although this AI cannot do good architectural design, but when I gave this climate conditions here in Hong Kong, as you can see, summer is very hot, right? Humidity temperature may be not like super high, 34 degrees, but our humidity is very high. You see the water bulb temperature can be 29 degrees. And sometimes which means our relative humidity is typically 70, 80, 90%. Okay, so therefore the cooling is a dominant one. Humidification is the most important. But interesting enough, the large language model gives a very nice ventilation system. You see here, we should use chilled beams, and which is a pretty advanced system. Water cooler, cooled chiller, of course, which has a much higher COP compared with the air-cooled chiller. And then demand-based ventilation, heat recovery, high efficiency air handling units, fan, etc. So it seems that the system the AI recommended is a lot advanced. Then, of course, I run the energy simulation again with this system. And then I find that we can reduce the energy use by 24.8%, as you can see on this right figure. And that's a lot exciting. You know, the architectural design doesn't save much energy, but the system design seems to be doing a wonderful job. So with that, and I say, well, that might be something we can explore a little bit further, because based on this one, the system design is a good one. But anyway, can we still change something on the building shape? Because I feel this design is really pretty boring appearance. Okay, and then some of you might be in my campus before. You know that on our campus we have a very famous building, which was designed by the Zaha Hadid. So Zaha Hadid is a very famous architect. She always designed a wonderful building. And the one, let the photo show in this slide is our actual building for the School of Design. So it's a very nice building. Many people come to our campus, always take a photo of this building. Okay, so I say, well, can you do something? I asked this computer large language model, Claude 3.7, can you do something with this style? And then, of course, the Claude generates something on the right side. As you can see, I don't think it's really Hadid style. So it seems the style design is not good enough, right? And I said, well, maybe you cannot do the Hadid style. Can you do Frank Gehry? So you see the photo on the right. This is a typical design of Frank Gehry. Frank Gehry always try to design dramatic shape of a building facade, as you can see on that photo. But of course, you can see this rendering here. This is from the Claude 3.7. It's not interesting. It's not really Frank Gehry. So then probably you can do something more conventional. For example, Jean Nouvel, who is also a very famous architect, and then the building appearance is not as dramatic as Hadid and Gehry. And that seems works somehow, but not ideal. As you can see on this photo, this blue is grazing and then brown is wall. I mean, this really doesn't make sense. You cannot design a building like that. But anyway, we just say that before I consider the structural support, let's look at the energy consumption. But you can see all this energy use is around 270 to 280, right? They are very similar, no matter what type of appearance. So when my student presented this result to me, and I say, well, that doesn't look as Claude 3.7 is a good one, okay? Because they fail to capture the significant features of this building aesthetic. And therefore, I told my student, I say, well, I see the building, I mean, like for example, JBDE can generate really beautiful pictures. And why don't you ask the JBDE to do the job? Then my students say, yeah, JBDE can definitely generate photos, buildings. But he said, okay, let's try it. All right. Then we asked the 4.0 because maybe Claude 3.7 is not a good one. So we use this JBDE 4.0. This is about 2 years ago. Okay. So at that time, JBDE 4.0 is the most advanced AI model. So again, you see the prompt I give is the same. But it definitely generates very nice photos. You see, let's say 3 different type of designs. Looks a lot modern. Okay, and I look at this one, I say, yes, that looks great. Let's take the one in the middle and then turn into energy simulation. But when you turn into a 3D model, in fact, it's not the one shown in the photo, but the one shown on the right side of this slide, as you can see here. So, and I said, how come? It's a 2 building doesn't look similar. You know, the one on the left is very chic, nice building. The one on the right is very conventional. Then when we do a little bit more analysis, we find that, in fact, the JBDE 4.0 cannot recognize the architectural details of the image. It generates the image like the one on the left, but it's just a photo. It doesn't know there's a wall, window, or shading. It doesn't have any sense. Just like if you don't know a particular language, and then I throw out a language to you, you just know, oh, it's language, but you don't know the meaning. So it's just like that, okay? And of course, the JBDE 4.0 can generate a lot of nice pictures. And then we just try to do a different one, okay? So you see, when we use the JBDE 4 to do the image and then convert it into 3D model, we have to use the Claude 3.7. It doesn't correspond to each other. The one on the right, it really look ridiculous because the window and the walls is somehow rendering arranges there. It doesn't. If you try to build this building, it will corrupt because the structure will not support that. Okay, so let's say it's not an ideal one because Claude 3.7 knows the window, the wall, the shading, the roof, etc. But JBDE 4.0, it doesn't know anything about this. So we find that these 2 doesn't correspond to each other. So we have to think a different way. Okay, so we later on there was a JBDE-5 is available there, but no matter it's a JBDE-5 or JBDE 4.0, they always generate is 2-dimensional images. It's not a 3D building. But of course, you can iterate to make this 2D image more beautiful to meet your requirement, but it's not a 3D building. But on the other hand, let's say due to the development in the AI field, especially in a large language, large vision model, for example, we use this Hunyuan3D. It's a large vision model, which can turn this 2D image into a 3D building model. And that sounds a good approach. And with this 3D building model, we can convert that to generate a energy plus compliant building geometry, and means you can use energy plus to do the simulation. So this is the idea, of course, the developer as the development of the AI models. But you can see here, we have to use quite a few different type of models in order to do the simulation. Now let's look at how 2D image is converted into 3D models by this Hunyuan3D. Okay, this is a large vision model. So unlike in the past, we start with a huge building. We just artificially generate a very small one-story, two-dimensional image by ChatGPT-5. Okay, you see this is a building with it's a 2D image. Okay, now by using Hunyuan, you generate a 3D shape. Okay, so although you look at the two images are very similar, but the one on the right, it contains the three-dimensional information into that. Because why? It's already can recognize the texture, all right? Because which means now we don't take this 2D image just like a photo. Now we could use Hunyuan to recognize their windows, walls, roofs, shapes, window frames, etc. So those are the basic building elements. And then, of course, it's a 3D dimension. It's a 3D building. So I like to see what happens on the back. Okay, so I turn this building 180 degrees, and you can see here, this Hunyuan is smart enough. It generates actually a door there. Because if this is a 3D model, and then there's all windows, no door, then this Hunyuan is not good, because you generate a building without a door, that's not a building. You cannot enter the building. So this, we didn't tell Hunyuan you should have a door there, but this Hunyuan can automatically recognize the needs and then generate a door on the back side. Okay, then of course it's a 3D. We have all the meshes there. What means mesh? Okay, let's look at the mesh. Mesh is shown in this slide, all right, which means I can identify the building elements. So as you can see here, from GPT-5, I use Hunyuan to convert it into 3D model. And this 3D model contains the windows, the exterior walls, the shading, and the roofs, right? So all the building elements is there. With those building elements, which means we can further turn into a energy plus geometry, which can be used for energy simulation. Okay, so let's look at the possible. Now we go back to the original idea. I wanted to design our building. Okay, so we use ChatGPT, and you can see here on the top left, this is a real photo. Okay, because the GPT now can read the image. So we give a photo. Oh, sorry. We give this photo to GPT-4 as the input. Okay. Then ask the GPT to remove the background element. As you can see, we have a lot of information here. Some other building in the background. Okay. So first you have to remove the unnecessary background element, the shadows, etc., even the trees, the surrounding structures. And as you can see, GPT can do it. Okay, this is the one. And you see top of middle picture has no other noise there. It's a lot of clean, right? And then of course this is a 2D image. This is generated by JBDE. And then we use Hunyuan to convert it into a 3D model. Okay, so you see Hunyuan generated a pretty nice 3D model, which contain more or less the same building elements as the latter picture. You see here, windows, walls, shading, etc. And then, of course, it's also generated a 3D one. So this is the 3D one. Actually, we only input one picture. Now it's generated into a 3D model, and compare with our current building, it's very similar. It's amazing. Okay, then of course, with the 3D model, I don't know what happened. Okay. With this 3D model, and then we convert it into the one which can be used for energy simulation. That's the bottom middle one. And you compare with our original design, you look at this wall window ratio, 0.52, area 16,000, and energy simulation result is shown to be 285.7, and the actual energy use, this is 286. I mean, it's more or less the same. So this is looks like a wonderful result, okay? Now you just give an image, you can do that. But of course, GPT has all the knowledge, right? Including many photos they read from the internet. Then I said, probably you get this right because many people take the picture from the back of the building and put it somewhere in their personal website or whatever. And therefore GPT learned that, or Hunyuan learned that. And then I asked my student to do something new, okay? I don't want to use a photo. So ask GPT-5 to generate a nice building, okay? Now you see this is a nice building, completely new. Probably you don't find this building anywhere in the world. But again, the prompt gave here is the total floor area, then it's 16,000, 18 stories high, and the window wall ratio is 50%, etc. So GPT-5 generated a nice, probably I think this building may be nicer than the one we have in reality. And then, of course, we process the image by use of Hunyuan, and then you have the 3D model. Okay, so that's the 3D model. This is supposed you don't see anywhere. Then you convert it for energy simulation. And as you can see here, final result, you get the window wall ratio 0.52, floor area 16,000, energy use, very similar. That looks nice. Yeah, now we can ask the AI to do this. Of course, now you see I use two different AIs. One is to generate the image by JBDE5, another to convert it into 3D model by using Hunyuan3D. Okay, then I can compare the two buildings. One is a real building on the left, one is a new building on the right, and then you can see, we save a little bit of energy. Okay, so let's since building shape, I already demonstrated in the earlier talk, the building shape doesn't matter very much as soon as you have a similar window to wall ratio. Okay, but look like AI can reduce 4.2% of energy use. Not much, but at least better than nothing. Okay. So let's say story about the building design. Now, then the next one, the question is how to make the system design. Okay, I'm not a structural engineer, so I didn't ask the AI to design the beams and columns, but I wanted to ask this AI to design the interior environment. And as Professor Chen just introduced me. I've been doing computational fluid dynamics at CFD for many years. So let's see if we could design the building with the CFD. I mean, design the indoor environment by CFD. Okay. So this is the flow chart. Okay, which means no matter you want to design the interior one, we again use GPT-4. We give the necessary information. Okay, I don't need you to read that. Just say I give the definition, and then look at how the building design. And then to simplify this, because building is very big, I just cannot show every room. I take one room as an example. Okay, so this is just a 2-person's office. Okay, and I give this window location. You see on the right, that's a window, and then I have 2 dummies here, simulated 2 persons, and it's a computer desk, and at the top is a lighting fixture, etc. Okay, so this is the information I feed into GPT-4. And I said, that's the information. And my objective is to design the thermal comfort, air quality, and also the energy efficiency. Okay. I wanted to have a very comfortable one, good air quality, and energy usage is minimal. So the design, of course, I wanted to design where should I put the HVAC system there, which means the air supply parameters, diffuser locations, number, and the type. Okay, now this is the design. In fact, GPT-4 cannot generate the image here. So at that time, we asked GPT-4 to generate the Python code. And with the Python code, we can convert it into this image. So you can see here, this image definitely follow our input. The window is here, that's 2 persons, that's the desk, and that's the lighting fixture is in yellow color. Now the design shows 2 outlets on the ceiling and 2 inlet. Okay, one on the back wall, another on the side wall. And that why for such a small building it generated 2 outlets, we don't know. And 2 inlets, we also don't know. Because typically we just need the 1 inlet, 1 outlet. But I believe why is have 2 inlet and 2 outlet? My guess is we didn't limit this number of the diffuser. Maybe 2 inlet is better than 1 inlet. Okay. And also give a very detailed information here. You know, what's the flow rate? What's the winter and the summer, the flow rate is different, and the air supply angle are also different, etc. That's interesting. Okay, so let's design, and then I said, well, can you just generate a flow distribution? But the flow distribution they are generated looks a little bit strange. And then I asked GPT-4, how do you get the flow distribution? It tell me use some empirical formula, which actually was derived in 1960s and 1950s, very old one, okay? And then I said, why don't you use CFD to do the simulation? Then GPT-4 say he cannot solve Navier-Stokes equation, so he cannot solve CFD. But of course, as a human being, we can solve the CFD. So this is the CFD my students solve based on these boundary conditions, diffuser locations generated by the GPT-4. So you see here, that's the velocity distribution on the top left. These are again factor. This is also velocity distribution on the top right. Then there's the temperature on the bottom left and the CO2 concentration on the bottom right. And you compare with the thermal comfort, air quality requirement, it seems that they meet our needs. So although GPT-4o doesn't know how to solve CFD, but by using the knowledge GPT-4o has, it generates something reasonable. Okay, so I'm very happy with this result. But when I look at the details, okay, because GPT-4 gives me all the numbers, and I find the calculation is wrong. For example, they use this heat gain. Okay, the top line here shows the heat gain. Use a heat gain as a cooling load. So for anyone who has studied the building energy transfer, heat gain is not cooling load because the building thermal mass will absorb the heat gain, and then there will be delay and decay and etc. and release back. The normally cooling load is smaller than the heat gain. That's the first conceptual why it is wrong. Secondly, I find the equation also GPT-4o use is wrong. For example, when I wanted to calculate the mass flow rate, GPT-4 forgot this rho density there. Furthermore, I find that the unit conversion is wrong. So those in red color is what I type in. Okay, in the black one, let's the GPT-4o generate. So which means that you cannot trust the GPT-4o calculation. So GPT-4o give me a flow rate on 141 cubic meter per hour. But I find that if I use the heat gain as the cooling load, my correct answer should be 506 cubic meter per hour. That's a huge difference. Okay, anyway, so let's say standing, I think you should be very careful about the number crunching by GPT-4. Okay, but of course, my objective doesn't just stop on the design. I also wanted to generate something which can be used for control. So for control, I have to use another large language model called Hunyuan. It's also a large language model, but it's a better one for control purpose. Okay, and then of course, if you do the thermal comfort study, typically when we do the thermal comfort, we use 7-point scale, which means very hot, warm, neutral, then cool, cold, very cold. But in reality, if you say cool, it's harder to determine how you define cool. Everyone might have a different perception of cool. And therefore, what I ask here is to input my real feeling. For example, I will say, yeah, I wanted to tune the temperature 1 degree up, and because it's a little bit too warm. Sorry, I will just give the control the direction here. Okay, no, my input is just say sorry here. I say it's a little bit cold, and the wind is blowing directly to me. Okay, which means I have some type of draft here. So as a result, Hunyuan will generate a control command, which say turn the temperature 1 degree higher and reduce the flow rate by 10%, and also change the air supply angle 5 degrees, and therefore I will not get the wind blowing directed on me. It's a very nice control command. And then, of course, you use this for the HVAC system input, and then you probably can get a much better thermal comfort in terms of predicted mean volt. So we use this, and this is the procedure, okay? Let's into a more general one. As you can see, this comfort, we have to put carefully indoor conditions to the desirable one. And then human beings have the preference, what type of comfort you want. And then, of course, we wanted to use less energy. And then use this as the input for Q1. And that Q1 will generate the output for the temperature change, flow rate change, etc. Of course, you can give more freedom to Q1, which will give you more command. And what we do is to validate this in our lab. So this is a very simple lab, one room. We put 2 desks there, as you can see, also 2 dummies there. Okay, we also measure the temperature distribution in several locations, right? And this is the boundary condition. And we try to evaluate the thermal comfort at the 3 different levels: ankle level, chest level, and head level for a seated person. Okay, and then we wanted to see how this control parameters is generated by Q1, which means it's air supply temperature, flow volume, and the angle. So typically, we also have the control by on-off or PID. All right, so you can see this is the energy use. Large language model can further reduce energy use compared with the PID if I use on-off control as the benchmark. All right, and this one is the comfort. On-off control typically is not comfortable enough, but large language model and PID, they can increase the comfort level. And this is a more detailed comparison in terms of PMV. 0 means neutral, very comfortable. -1 means cool, +1 means warm. You see on-off control normally has a very big deviation, and it's a little bit too cool, but the large language model and PID control can get a very good result. This is on the ankle level, this one is on the head level. All right. Now you look at the 20 this is the control over a period about 2 hours here. You see on-off control, your temperature too high, you switch it on, it go too low, you switch off, it getting higher again. So always swing, okay, around like the desirable 24. But if you use the PID control, of course, you can control the temperature much more nicer to be around the 25 degree. Large language model get a very similar result. Okay, so this is the temperature, humidity. Humidity, I think a large language model did the best. You see, you control to be about 58 to 59%. Large language, the PID control is a little bit too high, etc. Okay, here the velocity PMV. PMV, you see, always around 0. Is done by large language model or PID. Again, this is the ankle level, that's the head level. So now that's the work we have done by using large language model to simulate, to do the building design, and to do the energy simulation, and also indoor environment control. So from this result, you can see that the large language model can generate a very compressed 3D models and then can reduce energy use. Of course, you have to use different large language models. And amazingly, you know, my student finally find out you just use a 2D image and then to get the energy simulation through these different models, all can be done just in about 7 minutes of time. And currently, without the AI, if you want to do all this, it will take a few weeks of time. So this is a huge improvement in terms of the productivity. And of course, it can do the design on the air distribution, but one should be very careful about its illusion because it gives the wrong numerical output. But the HVAC system control, I think it is wonderful. Okay, so that's all for me. Thank you very much for your attention. And I would like to entertain if you have any questions.
Okay, thank you very much, Professor Chen. This is inspiring and helpful. And you teach us how to use the ARM modeling hand in hand. So now we move to the discussion panel. First, we just I ask Darren to give first comments for the speech.
Okay, thank you. So I think that was a real treat. I think a good measure of any lecture is whether you learned a lot from that lecture, and I feel like I learned a lot. So that was yeah, very thought provoking, and it's a very impressive ton of work that you've been doing on this over the last several years. So thank you very much. I have quite a lot of questions, but I'll try to keep them brief. So I've worked using simulation and optimization to support the design process in industry. And of course, I've helped students kind of understand and deploy those techniques in their studies. And my typical kind of approach is that I'm going to develop a base case model, and then I'm going to define my parameter space, and that parameter space might be comprised of both geometric and non-geometric parameters. And then I might, if the parameter space is small, then I might perform a series of parametric simulations using some kind of simulation engine. If the or multiple engines. If the simulation space is large, then I would use an optimization process, and potentially we can again use multiple simulation engines. We can perform multi-objective optimization, and I feel that the value of that is that somehow that computational workflow trains me or trains the student, because we're learning along the way, because we're able to somehow track the parameter changes, understand the relationship between those parameter changes and our objective functions. And I wonder if we're substituting those steps using a black box, whether we're possibly losing that learning, or we're losing the training from the workflow to the student or to the user. What do you think?
Yeah, well, thank you, Darren. It's a great question. Definitely, normally we do the job. We learn quite a lot in the process. And the large language model now currently is a black box. We don't really know what's going on there. Okay, so if we wanted to really learn something ourselves from this process, and then I find that large language model behavior is more or less like an expert, but a lazy expert. Okay, if you don't challenge a large language model, they will give you something rather simple. Okay, just yeah, you ask me this question. Yeah, that's easy. Okay, you just do like this. But when you challenge a large language model more, they will become more serious. They give you even better result. I didn't do a lot myself in the first part in terms of the building design, because I have no architectural background. But the one who did that is an architect. I mean, he trained as an architect, right? But I did involved in the second part when we designed the HVAC system. So first time I asked my student, now currently she's a postdoc at Harvard University. So she said, oh, large language model cannot produce a nice result. The system design is really boring and not good enough. But then I tried myself and I find that, yeah, you have to challenge large language model. So the deeper you ask, then they will improve that. For example, of course, you definitely see that the one they designed look like a displacement ventilation. And that is because I really said that I want to have a super indoor air quality, and which means on the displacement ventilation can do it. But of course, I also said I don't want it to be complicated, to get a complicated system. Otherwise, large language model might give me a personalized ventilation system, which is a very complicated one. So that's what I feel, we can probably can learn something through this type of interaction. But you should be careful. As I also show you, let's say illusions there. If you don't pay too much attention, you believe the data large language model generated for you, then you probably undersize the HVAC system, as you see in my analysis.
Well, so that leads nicely to my next question. So especially in the early work, but perhaps also to some extent in the later work, so there's been it's a very fast changing landscape, the
Yes.
Gen AI landscape. And I think what you showed us is that the use of AI, so there are different algorithms that have different strengths, and you need to rely on those different algorithms to play to those strengths. So it seems like it's slightly fractured at the moment. And
Yes.
you do, as you said, you do need a human in the loop to supervise that process, to make sure that you're getting something coherent. So I guess it's a crystal ball gazing question. When do you think we might be in a situation where that workflow becomes relatively seamless and essentially autonomous?
Yeah, I think it's a very good question. You can see I use a different type of models. Then how do I find those models? I don't know. My students spend a lot of time just to find out a suitable model, one for the 2D images, one for 3D vision, one for the data conversion, etc. It costs a lot of time to do that. But I currently I learn from my colleagues here who work specialize in AI, and I also have some limited experience. We find that currently many people just start to use the so-called small language model, or sometimes use this physically informed model, which really geared to, for example, energy simulation in buildings. So you just combine several large language models, take the useful features, and make it into a new model which is just specialized for a certain task. Because you see, like a GPT-4, you can use almost for everything. If a model is universal for everything, that means this model is not specialized. But if you try to focus, train this model just for one specific feature, just energy simulation, then they will do much better job because it's more focused. Large language model just like a human being, you try to claim to be an expert in mathematics, physics, chemistry, engineering, then probably you are not so good. But if you are just saying, I'm good in energy simulation, probably you are the top expert in the world. So I think
does that
the
mean
large
that
language model now have to turn into the small language model, and that's the direction to go.
Sorry to interrupt you there. So does that mean that your vision for the future is perhaps that we have a kind of master algorithm that is controlling, what the sort of child algorithms are doing?
Yeah, exactly. You need to get this small language model is more specialized. And then, of course, you don't have to go to find the suitable model here and there. If they already train this small language model just for specific field, then that's a good one. Yeah, there's already some work is being conducted in other fields on that way. And I believe sooner or later, we probably can find something similar in our field.
Okay. Let's let the Professor Yong to give a comments and join the discussion. So they will more good for him because he is also professional in the AI agents. Okay, Professor Yong.
Yeah. Okay, so thank you so much for your nice presentation and discussion with Darren. And I'm very impressed with your LLM workflow, especially including GPT, Claude, Huan. It's kind of the multi-agent system, I think. And you showed today the very various case study on building energy simulation. And I'm also studying about how AI agent can enable building simulation in terms of building design, operation, and digital twin. And I also published some research paper. And based on my experiences and lessons from my previous work, I think there are two important issues. The first one is how do you make sure the simulation reliability under the AI hallucinations? As you know, there are sometimes the LLM provide the long answer with the big hallucinations. So that is my first question. And the second one is, how do you think about the human expert role? In the future, if AI can do everything in terms of the building simulation and building design, what are the expert role in the future? So this is one of the big concern in our community. The final is for the simple question is how do you get the IDF converter? Is it made by AI too, or just used by the conventional, the converter? So I'm wondering Professor Chan's perspective on the concerns and the research issues.
Yeah, well, they are interesting questions. Okay, the first one, how do I know the AI is doing a good job or the data is reliable? And I think we had learned a pretty hard lesson. When I look at the HVAC system design, and the flow rate looks small. And of course, I've been doing this for a long time, and I know that something looks incorrect. That's why I discovered it. But of course, for a new user, probably don't know that. And that's why you see when we compare, when we do the energy simulation, you probably remember in one slide, I show manual calculation. Let's say when we have done the final design, then we use a conventional method, just like what we do currently without AI. So I just build step by step in those EnergyPlus to do the simulation and to get the result and compare with the AI final result and see if they are close or not. If they are close to each other, then yes. The similar one, we use the CFD to verify if an AI design is good or not. So I think this validation, no matter it's by manual calculation or by experimental measurement or whatever is essential. So you cannot just believe anything generated from a black box currently, like a large language model. I really feel it's very dangerous. You trust 100% AI result. AI definitely has an illusion, and it happens very often. So that's what our experience. Now, the second question is, if AI is so capable, then what is our job future? And I think this is a very big question. You know, many people are just wondering what's going on. You look at the computers, the scientists, many people who study in the computer science, now they are out of a job. Because many simple jobs can definitely be done by AI. There's no doubt. You look at the one I show here, 7 minutes, you get the build from scratch to the energy simulation. This is unprecedented speed. Even a very smart professor like Professor Robinson here, I doubt if he can do that in 7 minutes, right? So it improved the efficiency. So last week when I was at the University of Cambridge to give the presentation, then a group of architects there, they asked me the similar question. So what's their job future? Because you look at the architectural design by JBDE 5 looks a lot innovative. So I really cannot answer this question because I really don't know. I think everyone has a certain type of anxiety about the capability of AI. Will they really take our job away? Or this is just a big bubble? After 5 years, AI bubble bursts, then we are back to normal. So I really don't know. I cannot answer this question. So what's the last question again? I just forgot.
For the IDF converter you used. So I'm wondering how you get the IDF converter from your 3D geometry to the EnergyPlus input file. So is it made by AI to AI
Yes, but
or
it's made by AI. We just give it a prompt. Of course, when we convert from 2D to 3D, okay, first I asked my student to develop our own program to convert from 2D to 3D by using a lot of images to train, because if you wanted to train a 3D model, you have to use a lot of images. So we done that for half an year. Then later on, we found that already large vision model, Hunyuan, which already been trained. So they are professional trained much better than we. So that's why we switched to Hunyuan. So we have a lot of the lesson learned during this process. Sometimes we don't know. I think the AI has been developed so rapidly. You need to study to do the literature search every other weeks. Otherwise, you might left behind. So that's also a very good lesson we have learned. So maybe something today looks impossible. Next week it may be possible. So that's what we learn. But of course, some of them likely generated output for EnergyPlus. If you use EnergyPlus, that's a lot of parameters, right? So will the AI really convert everything correctly for EnergyPlus? We didn't know. We didn't check it in detail, but we usually manual calculation to compare the case I show you look so pretty close to each other. But it doesn't mean the AI converted everything correctly. Sometimes, you get one part wrong, another part wrong, but maybe one is negative, another is positive, but then eventually you even out, you get a good result. Maybe just we are very lucky. So this is something we are not so sure.
Okay, thank you for your insight and good answer to me. Thank you.
Thank you, Professor Chen. Just one audience said, ask a question. Just to let your comment, what's the PINN, the model to use to simulate airflow, the potential in the simulation, or use it, use the, there just, do you see the value of the PIN in embedding physical constraints like field central limits or daylight factors as a software guide into the generative process to keep AI creative yet physically grounded? Yeah, it's in chat.
Okay, in the chat, which question? On the live channel, how can generate AI intelligent manual model? Yeah, I think the question I already somehow answered to Professor Young's questions there. Yes, I think the generative AI, because it still is a black box model, right? We use that, it seems we get a reasonable good result. But if this result is seamless or not, I'm not so sure. On the other hand, the traditional result sometimes can be, because when you work out something on the traditional way, you also can make mistakes. So I'm not so sure which one will be better. But of course, if you can use the AI and then the traditional way to compare each other, probably will be the best one. Yeah, I see also there's another questions asking the large language model. We typically use a skin temperature measurement as the ground truth to supervise our models. And we have been exploring PINN to enforce the physical laws. On the energy simulation side, do you see value in embedding the physical constraints like heat transfer limit, dating factors, etc. in the process? Yes, I think definitely the answer is yes. We always need to put more limits, especially the physical informed models, and which will really improve the simulation efficiency a great deal. That's our experience. Because when we ask AI to calculate, for example, to do the flow rate calculation, and then we find that the equation they use is really out of date. And if you could supplement that with the CFD, of course, will be much better. But then that's answered next to the next question. CFD is very slow, and boundary condition is uncertainties, and how could the surrogate model with the lower efficiency, how this help each other? Yeah, recently we work on, for example, combination of outdoor airflow and indoor airflow together. And when you do the combination of outdoor airflow and the indoor airflow, because of the scale and also the complexity, and really computational cost by CFD is way too high. We cannot really to get the solution from the CFD. But by using the PINN, we improve our surrogate model. Originally, it's just a polynomial form of the surrogate model, and that will really improve the efficiency. We already see from our simulation for the combined indoor and the outdoor airflow. But of course, in today's presentation, I didn't show the result. But I definitely agree with it's a problem. Yeah, I think the person who asked is Xian Chen. Yeah, I think he or she really asked a very good question. Yes, the answer is you need a PINN to improve the model.
Okay, thank you,
May I-
Professor. Oh, I have a last question. Okay.
I am sorry. I think that last question was very helpful, and maybe it would be really helpful to have some guidance on the scope of applicability of different types of algorithms. So I can see the value of LLMs in generating initial models, but I totally get that something like physically informed neural nets is a more reliable way forward when it comes to emulating a physical simulator. And of course, we can use other types of surrogate for to emulate the optimization process, so that we have a relatively seamless overall workflow. So it'd be great to have some thoughts about whether guidance could be produced to better understand what the scope of applicability of different types of algorithm is.
I agree with you. I mean, currently, all these generative AI models are still in the infant status. We are trying to use that to help us, but we probably have not explored the full capacity of those models. This one on one side. On the other side, because those models might not be trained to fit our needs, right?
Mm-hmm.
We typically don't put everything on the internet. So if you don't put everything on the internet, the AI cannot learn from that. For example, we often just publish our final result. We have a lot of data hidden in our own computer desk, so AI cannot read that. So I believe this you are right. This is something we definitely need to explore further.
Thank you.
Okay, thank you for Professor Chen. Yeah, the impression for me, you can just get an AI assistant to do architecture for the energy plus simulation and city simulation. You are expert. You can find any problems, but for the architecture, you just find a very easy assistant to solve some problems. So it's also just inspire me. We can find some assistant from different specs, different disciplinary, and then we can do more broad research. So it's my feeling. So thank you, Professor Chen. And due to the time, so we have to close the session. Thank you, Professor Chen. Thank you, Professor Robinson and Professor Yong. And thank you all audience. Thank you very much.
Thank you. Bye-bye.
Okay, bye.